So part two begins signal processing practice final exam number 3. Let x of t equals t e to the negative a times a square times a absolute value t where a is greater than 0. For part A, determine x of omega. So this is a continuous Fourier transform problem. So to find x of omega, x of t equals t e to the negative a, absolute value of t where a is greater than 0, e to the negative a, absolute value of t, that transforms to 2a over a squared plus omega squared. So from the Fourier property, we get this transformation here, t x of t, that transforms to j dx of omega d omega, where x of t equals the following, t e to the negative a times the magnitude times the absolute value of t. So x of omega equals j d dw of that 2a over a squared plus omega squared, ddw of 2a of a squared over a squared plus omega squared. That's going to equal negative 4a omega over quantity a squared plus omega squared quantity squared. So we're going to get x of omega equals negative j 4a omega over quantity a squared plus omega squared squared. For part B, they want us to determine the magnitude spectrum. So the magnitude spectrum is just going to be 4a absolute value omega of over a squared plus omega squared squared. For part C, determine the phase spectrum. So the phase spectrum, since x of omega is purely imaginary, for omega is greater than 0, x of omega equals negative j positive. So the phase is negative pi over 2. For omega is less than 0, x of omega equals positive j positive. So the phase is positive pi over 2. And then for here, the angle of x of omega equals this piecewise positive pi over 2, where omega is less than 0, and negative pi over 2, where omega is greater than 0. And it's undefined at omega equals 0 because the magnitude is 0. For part D, they want us to find the bandwidth, where the magnitude falls to half maximum. Okay, so for part D, so sorry. So half maximum bandwidth for omega is greater than 0, absolute value of x of omega, that equals 4a omega over quantity a squared plus omega squared squared. Finding the maximum, we let f of omega equal omega over quantity a squared plus omega squared squared. Taking the derivative using the quotient rule, we get a squared plus omega squared squared minus 4 omega squared times the quantity a squared plus omega squared over a squared plus omega squared to the 4th. That's going to become a squared minus 3 omega squared over the quantity a squared plus omega squared cubed. Setting the numerator equal to 0 and solving for omega, we take the positive value. Omega is a over the square root of 3. So the maximum is going to occur here at omega sub max is a over the square root of 3. For the exact half maximum points, we're going to solve 4a omega over quantity a squared plus omega squared squared. That equals 1/2 times quantity 4a times a over the square root of 3 over a quantity a squared plus a squared over 3 squared. We're going to let r equal omega over a. We're going to solve r over 1 plus r squared squared. That equals 1/2 times 1 over square root of 3 over 1 plus 1/3 squared. Okay, so the equation is quartic in r, normally solved numerically. Half power points are obtained from r over the square root over the quantity 1 plus r squared squared equals 9 over 32 times the square root of 3. So we're going to get omega is about 0.172a, omega is about 1.386a, and the positive frequency 1/2 max width is about 1.214a. And for part E, they want us to discuss how increasing A affects the spectral width. So the effect of increasing a larger A makes e to the negative a absolute value of t decay faster in time. So the signal becomes more localized in time. And by the time bandwidth principle, the spectrum broadens. Okay, so that's number 3. Moving on to number 4. Okay, so we have an analog frequency, has the following components here. For hertz, 100 hertz, 350 hertz, 700 hertz, 1200 hertz is sampled at f sub s equals 1000 hertz, is sampled at f sub s equals 1000. Sorry, wrote that twice. Determine the Nyquist frequency. So this is sampling theory and aliasing. So the frequencies here, 100, 350, 700, 1200 hertz. Sampling frequency f sub s equals 1000 hertz. So the Nyquist frequency f sub n equals f sub s over 2. That's 500 hertz. F sub n equals 500 hertz. The frequencies for part B, which frequencies alias? Frequencies that alias, any frequency above 500 hertz aliases. 700 hertz and 1200 hertz. For part C, determine the observed alias frequencies. Alias, some people say alias. Alias observed frequencies, it's going to be f sub alias, absolute value of f minus k, f sub s. That's chosen to lie in the interval 0 to f sub s over 2. So for 700 hertz, absolute value of 700 minus 1000, that's 300 hertz. For the 1200 hertz, absolute value of 1200 minus 1000, that gives you 200 hertz. So therefore the observed frequencies are 100, 350, 300, 200 hertz respectively. 700 goes to 300 hertz, 1200 goes to 200 hertz for letter C. For letter D, find the minimum sampling frequency preventing aliasing. So for D, minimum sampling frequency preventing aliasing, the highest component, f sub max equals 1200 hertz. The Nyquist criterion, f sub s is greater than 2 f sub max. For f sub s, that's greater than 2400 hertz. F sub s greater than 2400 hertz. And the minimal ideal rate is 2400 hertz, with practical sampling slightly above. And for part E, describe an ideal anti-aliasing filter. So here, anti-aliasing filter, before sampling at 1000 hertz, the anti-aliasing filter must remove frequencies above 500 hertz. Here's our ideal filter, h of f, piecewise of 1, where absolute value of f is less than or equal to 500 hertz. 0, where absolute value of f is greater than 500 hertz. So the ideal low-pass cutoff here is 500 hertz. And in practice, the cutoff should be slightly below 500 hertz to allow transition band. Okay, that is number 4. Moving along to number 5. Number 5, consider this system that we're given here. Here is our input. Those are deltas. Sorry about the way they're drawn. For part A, find the system function h of z. So discrete time convolution and difference equations. So we're given this system function here. What we're going to do is we're going to take the z transform of it as follows. We're going to get the following: h of z is y of z over x of z. So we're going to get 1 over 1 minus 6 tenths to the negative 1 plus 8 tenths to the negative 2. Factoring that becomes, that denominator becomes 1 minus 0.4 z to the negative 1 times the quantity 1 minus 0.2 z to the negative 1. So h of z is 1 over quantity 1 minus 4/10 e to the negative 1 times the quantity 1 minus 2/10 e to the negative 1. Part B, find the poles. Poles are going to be at z equals 0.4 and 0.2. For part C, they want us to determine the causality for part C. So what we could say for part C is causality. If the system is causal, and I spelt that wrong. Sorry about that misspelling. The ROC is outside the outermost pole. Absolute value of C is greater than 0.4. The difference equation written in present output and past outputs is naturally causal. So the causal of ROC, absolute value of Z is greater than 4/10. For part D, they want us to find the impulse response. Impulse response, we use partial fractions here. For this, we perform all the computation. So for the causal ROC, this h of n, that's going to give you 2 times the quantity 0.4 to the n minus 0.2 to the n, and then that times that u of n there. So that's what we get for letter D. And for letter E, compute the output sequence. So here's the output for it. That x of n equals delta of n plus 2 delta of n minus 1. Because the convolution with shifted impulses gives that y of n equals h of n plus 2h bracket of n minus 1, close bracket. So y of n here equals quantity 2 times 0.4 to the n minus 0.2 to the n, parentheses u of n plus 2 times quantity 2 times 0.4 to the n minus 1 minus 0.2 to the n minus 1 times that u to the n minus 1 in the brackets. Okay, so that's part 2. Thank you very much and have a great day.